thank you, Christoph, and the organizers to host me in this video conference. It's a strange feeling for me, even after 1 year of having lectures video screened and not seeing real students most of the time. But let's do our best. And in any case, if you have questions, feel free just to ask. Actually, I think this makes it more comfortable for me to have some interaction in the meantime while I'm speaking. So before I really start with the talk, I feel somehow that I should make some comment on the conference, which was planned originally for last year, September. Then we postponed it due to the pandemic to this spring. And it soon turned out in last year already that this is still not a good idea. So in the end, we had the opportunity to postpone it even further to September this year. And we very much hope that in the end, this will turn out to be realistic. And I can at this point only promise to keep you informed and check the situation regularly in Germany, but also in the neighboring countries where the participants should come from, to see whether we can really do that at the conference venue in Bad Herrenalb. And because I think honoring Rolf and Wolfgang would not be the same if we just had video contact. So this should really be an event where we meet in person. So this talk is about tessellations, or more specifically about random tessellations. And I will start very gently, in particular in Euclidean space, and say something about hyperplane or line tessellations in the beginning there. But then I will give a brief introduction to what I understand about hyperbolic geometry, which is needed in the following, just to make some of the basic concepts available for the study of mean values, variances, central limit theorems, which are the main topic of this talk. And if time permits, I will also finish with a teaser on Kendall's problem in hyperbolic space. So mosaics or tessellations provide a very interesting and applied also topic which is suitable for applications. For instance, if you want to model telecommunication or street systems, this is the very first and rough approximation. But of course, this would be too simple, and therefore often you combine various models or nest models one into the other to make it more appropriate for applications. But in this talk, I will have mathematics in mind, and for us, a tessellation in general is the decomposition of space. Usually the parts are considered to be convex or even bounded. But this need not be the case. So we could have actually unbounded components, and we could have even non-connected components. So the division of space in a tessellation can be obtained via hyperplanes, which dissect the space, and hyperplanes have to be understood within the ambient space in which we work. So in Euclidean space, this is quite clear what hyperplane means. In spherical space, these are the great subspheres. And in hyperbolic space, there's also a natural concept. And of course, more generally, you could consider totally geodesic submanifolds, say, of codimension 1. Other decompositions of space could be via Voronoi cells, or some other types of subdivision processes. And randomness comes into the game if the objects you started from are chosen randomly, say the hyperplanes are selected randomly, the points which define the Voronoi cells are random points, or the subdivision process is done according to some random selection procedure. So I said that we might consider tessellations, in particular hyperplane tessellations in various spaces. But so far, there are not so many results available, say in spherical space. Most of these are quite recent. And in hyperbolic space, there's even fewer results available, and most of the time they are restricted to the hyperbolic plane. On the other hand, there are many activities also in other spaces, in particular in hyperbolic space recently, concerning random graphs, random polytopes, floating bodies, variants of the Boseman-Petit problem, and related or unrelated geometric inequalities. And of course, I could mention plenty of names here, especially in on the last item, by people who are, I guess, and I've seen in the audience, but I will rather move on. So here's a short selection of some typical questions which have been dealt with in the context of tessellations or random polytopes. So what you usually study are phase numbers, the so-called F vectors, either of individual cells or some kind of statistical average cells. You could consider other quantities like the volume of the cells, of their phases, or certain functionals of the cell boundaries. On the other hand, you might not only be interested in mean values. Of course, you want to study the deviation from the mean by studying the variance, say, or you want to do some asymptotic analysis. And this can not only be done for the functionals I mentioned, but also for shapes of the cells, be either big cells or small cells, which have been considered. And you could even go further and ask for whole distributions of functionals or cells in some asymptotic regime. Other topics which come to mind, which are also quite recent, is percolation, say, with respect to tessellation models. So why should we care about hyperplane tessellations? So for me, that's a very basic model, of course, but one which belongs to the ones which one should and has always studied first, together with the Voronoi tessellations, say, the duals of them, and more recently, so-called splitting tessellations. And I think that they combine nicely various aspects ranging from combinatorics to geometry and probability. And what sometimes makes them difficult in the analysis is they exhibit certain kinds of long-range effects. And what you see on the right side in this picture is something I enjoyed discovering on the streets of the city Budapest. So we consider hyperplane tessellations, or what you see here is rather a line tessellation in the plane. And actually, you don't see the whole thing, but you only see a certain part of it within a round observation window, a circular observation window. And questions you might be interested in could be concerning the total edge length of the lines within the observation window. So everything you see in red here, you could ask for the total length of these red segments. Or you could study pairwise intersections of these lines within the observation window. And then you get collection of intersection points. And once again, you could ask for the number of these intersection points within the observation window. In Kendall's problem, what you then study is, again, in the plane and in a random scenario, of course, but basically you consider a certain cell, say the one which contains a specific point, like the origin, and let's call them the Crofton cell. Let's call it the Crofton cell, and ask for its shape. So the red shaded or red area in the middle of this figure, and ask what kind of shape this should have if it's large, or under the condition that it's large. So this is this kind of shape information I was talking of in the beginning. So let's get back to the original problem, namely intersection processes in Euclidean space. And when we talk about processes, then we have to define the random setting in the background. So what we will working with is a Poisson model, and this can be defined quite generally. And in fact, it's convenient to introduce a Poisson process in a rather abstract manner, namely in some arbitrary measurable space X, together with some sigma field and a measure mu. There's only a minimal requirement, some kind of finiteness condition on X, which you need. And then we say that a point process eta, so a random collection of points in the space capital X, is a Poisson process with respect with intensity measure mu if the number of points, so this eta of b, follows a Poisson distribution with parameter mu of b. So this should depend, of course, on the test set b. And if the random variables, the real-valued random variables, which count the number of points in disjoint sets b1 up to bn, if these random variables are independent. So if you have such a set B and you count the number of points in B, this should be a Poisson random variable, and you have sets B1, B2, and B3, which are pairwise disjoint, and count the number of points, then these should be independent random variables. What we will find useful in the study of the functionals we are interested in is the concept of a Poisson U statistics, which is based on the underlying Poisson process eta. And this can be defined in the following form. So suppose you have some function f on k tuples of points, x1 up to xk, which is symmetric and of course measurable and perhaps also integrable with respect to the k-fold product measure of the underlying measure mu. Then we sum overall pairwise different points x1 up to xk from eta. So that's the meaning of this notation down here. We evaluate f at these chosen points. And then in order to avoid useless repetition, and because of the symmetry of the function f, we divide the whole thing by k factorial. So what we get then is a function capital F of eta, and this is called the Poisson U statistic. The function little f, which is the main building block, is called the kernel of f, and the number k, which is also crucial, is the order of the U statistic. And let's see now how the total edge length of this Poisson line process. So in this case, capital X is the space of lines in R2, or more generally, the space of hyperplanes in RD. And F1 has to be defined properly. So we'll do this on the next slide or subsequent slide. So we have to explain how we can do little f so that this functional f we are interested in is of this type we just defined, namely a Poisson U statistic. So that we can actually see the total edge length as Poisson U statistic of the underlying Poisson process, and also the number of intersection points. And here you can see that it was useful to consider Poisson U statistics of order k. So this number of intersection points will certainly be a U statistic of order 2, because you need to consider pairs of lines. To explain this in more detail, still in Euclidean space, and for hyperplanes in RD, we denote by A sub D comma D, the space of affine D minus 1 planes, so hyperplanes in RD. And since we need to define an intensity measure mu, which is here denoted by mu sub D minus 1, we do this here in this line. So we evaluate mu D minus 1 in a measurable set of hyperplanes by checking whether the hyperplane, which has direction L, and then you choose a point X on this line, and then you take the orthogonal complement. Then if this is X, this is HL, comma X. So that's what we mean by this. Then we check whether HLX is in B, integrate over all points X from the line through the origin, and then vary over all directions with respect to some, say, invariant measure on this one-dimensional linear Grassmannian. So this could be the intensity measure of a hyperplane process. And then, of course, the Poisson process having this intensity measure mu D minus 1, or rather T times mu D minus 1, because we want to say that we want to slightly you want to be able to say that we have a higher density of lines in the space, and this is done by this multiplier T. In fact, I should point out that a Poisson process not only exists for a given measure mu on the space, but it's also uniquely determined in distribution by this measure. So in some sense, the Poisson is completely and uniquely defined by prescribing this intensity measure. Now, how does the U statistic look like if you want to describe the total edge length within an observation window or the number of intersection points in an observation window? So for this, we start with an observation window W, which should be a convex body. We prescribe the dimension of the intersection process, which is I in this case. And then we sum over all D minus 1 tuples of mutually distinct hyperplanes from the Poisson process eta T, take the intersection of all those, intersect with the observation window, and take the volume, the I-dimensional volume, or the I-dimensional Hausdorff measure. And this was the K factorial in the beginning, now K is D minus I. In the special case where W is a ball of radius r, we use the simplified notation you can see here. So it's not too hard to determine the expected value of, to determine the expected value of any of these intersection functions fi within a ball of radius r for a given intensity t. It's already harder to determine the variance. What is shown here is a central limit theorem, which goes back to Cathy Parou from her thesis in '97. And she treated the two-dimensional case, so the Euclidean plane, where you have the total edge length and the number of intersection points with an observation window. And much later, Lothar Heinrich and two colleagues from Schmidt, from Ulm, among which is Volker Schmidt, they showed the channel dimensional case and all indices I between 0 and D minus 1. Here, as you may have expected, n is the standard normal distribution. So this provides a central limit theorem for the functionals we are considering. The approach by Cathy Parou was via the method of moments. In this later paper, Heinrich and Schmidt, they considered Höfting's decomposition available for U statistics and the corresponding CLT. And whereas here still the balls as observation windows have been considered, this was later generalized to channel observation windows by Lothar Heinrich. Also observe that in this case, T, the intensity of the underlying Poisson process, is fixed, whereas the radius or radius of the balls is expanding. So the limit is with respect to R going to infinity. Okay, so here's this R going to infinity. Even more recently, the previous result was channelized in various directions by Günther Last, Matthew Penrose, Matthias Schulte, and Christoph Thiele. They had a general kind of statement saying that if you have a Poisson U statistic F, as the one we had seen before, with respect to some underlying Poisson process with intensity T, and if the kernel F satisfies certain integrability assumptions, then the scaled functional F, so the normalized functional F, satisfies a central limit theorem actually with convergence rates. So here you consider T going to infinity, and D is some metric on distributions, on probability measures like the Wasserstein metric or Wasserstein distance. And then they showed not only a central limit theorem, but they showed that this converges with the order 1 over T squared. And their result is on one hand extends, but is also crucially based on previous work by Matthias Reitzner and Matthias Schulte. And this is also covered in the PhD thesis by Matthias Schulte. In looking at the previous case, where we considered a number of intersection points or the I-intersection process from a hyperplane tessellation within an observation window, and considered R the radius of the ball going to infinity, whereas here the intensity is going to infinity. It should be pointed out that the two approaches are equivalent in Euclidean space and for functionals F which are homogeneous. So the cases which we are having in mind, namely volumes of intersection process observed within an observation windows, they are completely covered by the result you can see here, because they satisfy this nice scaling behavior in Euclidean space and the homogeneity. So after this rather lengthy introduction, let me move on to hyperbolic geometry. So what we mean by a hyperbolic space is a complete simply connected space of constant curvature -1. And I simply say it's a hyperbolic space or standard space of constant negative curvature -1. If one wants to visualize this, there exist various models like the hyperboloid model, the half-space model, the conformal ball model. So these two being associated with the name of Poincaré, or another model which is often useful for convex geometers coming from Euclidean space, namely the projective disk model, because in this model, convex sets look like convex sets, and lines or planes look like planes in the Euclidean space as well, but restricted to an open unit ball, say. In all these models, you can identify the isometry group, which acts transitively on the space, and hyperbolic space has a nice property which we all miss at the moment, namely it satisfies the axiom of free mobility. Depending on the model of the hyperbolic space, there are different representations of the metric, so the distance between points. So I used an dh to denote the distance. So here is, for instance, a description of the hyperbolic model in the hyperbolic space in the conformal ball model. And it shows that whereas this goes to infinity and the cosine hyperbolicus of this distance goes to infinity, the points x and y stay within the open Euclidean ball. But this fits nicely together because the points x and y, or say x is the origin and y goes to infinity, corresponds to x going to 1, say. In hyperbolic space, we can consider metric balls, so geodesic balls of radius r, and their volume is described here by the common formula involving the sinus hyperbolicus raised to the power d minus 1. And this behaves asymptotically like this as a function of r. But if you see this for the first time, this is certainly surprising that also the surface area of the unit ball of the ball of radius r has the same asymptotic behavior. Of course, when we want to study the analogous concepts in hyperbolic space, which we had discussed for the Euclidean space before, then we need a measure on the space of flats, so hyperplanes in hyperbolic space, so which are totally geodesic submanifolds of codimension 1. And in depending on the model, as I said, they look like the Euclidean ones, namely in the conformal disk model, or they look as you can see here. So this will be a hyperplane. Also, this will be a hyperplane in some other model, namely sorry, this is the conformal ball model, and in the projective disk model, they look like in the Euclidean space. But what we need is for general K-planes a measure which is invariant under the isometry group. And here you can see it. It looks rather similar to the presentation from the Euclidean space, but there's some significant difference. So here we also integrate over the corresponding Grassmannian, so which is linear Grassmannian like this here. But once you choose a point on this, which might be this one, we take the hyperplane orthogonal to it. So this is what we had considered before, only that it looks differently now. But the main difference is that here we encounter an additional density, namely the cosine hyperbolicus raised to the power k, depending on the distance of the point x from the origin. So we could consider any point P as the origin, but let's take the one which is the origin of the Euclidean ball from the model we are considering. In the special case, when k is d minus 1, this simplifies slightly, because then we can start with the direction u, starting from the origin, and going a distance r, we end up with HUR. This is the hyperplane in direction u, having distance r from the origin. And as you might know, it hits orthogonally the boundary of this unit sphere. So these are all the ingredients we need in principle to introduce Poisson processes of hyperplanes in hyperbolic space. And that's what we do now. So we could simply say, let eta t be a Poisson process of hyperplanes in hyperbolic space with intensity measure given by t times the isometry invariant measure on the space of hyperplanes. So t mu d minus 1. And this is the invariant measure, and this is the intensity. But this is rather abstract, so let me give an alternative description, which hopefully is instructive. Namely, we could start with a point process, a Poisson point process on the real line, so on R. And the Poisson points are these Ri, these are real numbers. And this Poisson process now should be inhomogeneous, should it should have this density here with respect to Lebesgue measure. So it has the density intensity T built into it, but it also has a weighting with respect to the distance from the origin, which grows quickly, namely like the cosine hyperbolicus raised to the power d minus 1. And once you have these Poisson points Ri, there are infinitely many, you attach to each of these random direction ui independently of each other and independently of the Poisson points from this x naught. And then in direction ui, you choose the point Ri times ui and take the orthogonal sphere to it. And the collection of all those is precisely a Poisson process having this intensity measure. So this is somehow a more specific way of describing a Poisson process of hyperplanes. And the two pictures which you see here and there, they show realizations of such a Poisson process with low intensity on the left and high intensity on the right. What you can also see is that these hyperplanes, they seem to somehow accumulate on the boundary, because that's where you go if you go out infinitely far. And most of them will have empty intersection. So that's quite different from our Euclidean experience or from the spherical space, say. So we are still collecting in ingredients, and we find useful in dealing with intersection processes in hyperbolic space. And as you probably know, already in Euclidean space, tools from integral geometry are crucial. Here's a quite general and useful result, namely a Crofton formula in hyperbolic space, which was already discovered in '66 by brothers. And it's stated in the following way. So we have a d-dimensional hyperbolic space. We have some indices I and k between 0 and d minus 1, I is less or equal k. And we have a set W, which should be considered as having dimension d plus I minus k. So this would be the intersection dimension generic of a flat of dimension k and a flat of dimension I. But we do not say anything like that. So this is just a set having this dimension, and it's rather general. So it's a countable union of Lipschitz maps of Euclidean spaces of this dimension, or of hyperbolic subspaces of this dimension. And now what we do is the following. We have this set W, we intersect it with a K flat in hyperbolic space and take its I-dimensional measure. So that's the generic dimension. If you intersect the set of this dimension with a K flat, the intersection would be expected to have dimension I. We take the I-dimensional Hausdorff measure, or volume of it, and average over all K flats. And the result is the measure of W in the right dimension, namely d plus I minus k. There is some correction constant here, but for instance, in the special case when I is equal to k, so this k is the same as the exponent I in this particular case, then W is a full dimensional set, so it's a d-rectifiable set, and this means any Borel set in HD is admissible. Then the right-hand side is just HD of W, so the volume of W. And well, this result holds in hyperbolic space, but it holds also in Euclidean and spherical space. And the class of sets which are considered here are essentially the most general ones. Okay, so now we will come to normal approximation of Poisson U statistics, but let me ask at this point whether there are any questions so far. Because I can't see you in this, when I share my screen, I do not hear any questions, so I will continue. So here's a general result, which actually was also at the basis of the result I mentioned before by Günther, Last, Matthew Penrose, Matthias Reisner, and Matthias Schulte. So it was a previous result by Matthias Reisner and Schulte and Matthias Schulte. And it states if you have a Poisson U statistics with respect to a Poisson process with intensity T, kernel F, and of order K, and then you can bound, say, some Wasserstein or Kolmogorov distance of the normalized functional Poisson statistic F from the normal distribution in terms of certain quantities, which you can see here on the right-hand side. So these quantities involve, on one hand side, the variance of the Poisson U statistic, but also some other ingredients which are not defined on this slide and which seem to be, well, of course, they depend on the kernel F, and they depend on some indices U and V, which are summed from 1 to K. K is the order of the statistic. But otherwise are undefined at the moment, and I will leave them undefined until much later. But it's becoming clear that when you want to prove a central limit theorem, you should ensure that this right-hand side goes to 0. And if you can bound this nicely in terms, say, of the intensity, say, or some other parameter, then you also get quantitative versions of central limit results. And that's precisely what was done in the Euclidean space, in which we are doing in hyperbolic space as well. I should mention that this was a very nice idea, which was based on a Maillard calculus on Poisson space, chaos expansion of U statistics, and in particular on previous work by Giovanni Peccati and Solé, Takun, Utzet, who combined the Maillard calculus with Stein's method. So here's again a description of the intersection in the functional described as a Poisson U statistic with kernel F. Recall that eta T is the Poisson process. We take D minus I tuples of hyperplanes in hyperbolic space. And the kernel is given in this way. So we take the intersection of D minus I, a pairwise different hyperplanes. We intersect it with the observation window, say a ball of radius R, a geodesic ball of radius R. And then we take the volume described here in terms of the I-dimensional Hausdorff measure. Of course, in many cases, this intersection will be empty in hyperbolic space, and we only want to consider actually when this intersection is non-empty, so if it has the right dimension, which is I. Actually observing that this will be 0 anyway if the dimension is lower dimensional, and that higher dimensional intersections are negligible in the probabilistic setting, we could drop somehow this indicator function. So when you think of the central limit theorem and the normalization which is done there, the first step will be to determine the mean number, so the expected value of the functional fi. And here is a nice formula which says that the mean of the functional fi, so the I volume of the d minus I fold intersections of hyperplanes in hyperbolic space with an observation window W and a given intensity T, is up to a constant the volume of the observation window, and here is a polynomial, a monomial given by this power T to the d minus I. In particular, if we just consider the volume of the flats, so we take I equal to d minus 1, which means that we do not intersect the hyperplanes with each other, but just take the volume of the section plane within the observation window W. Then this is linear in T, and the constant is just turns out to be 1. And for the other values of I, asymptotically, as the dimension goes to infinity at least, this behaves similarly. I should also mention that the formula is exactly the same in Euclidean space. And this is not surprising if you look at the proof, which I have outlined here. So recall that Fi is an intersection over d minus I tuples from the Poisson process. And the multivariate Mecke formula is a general tool which allows to calculate such mean values of factorial moments of the Poisson process eta. The main thing you need to know is that the intensity measure of this factorial moment measure, let's call it, is just the product measure of the intensity measure of the corresponding order, namely d minus I, which leads to the power t to the d minus I. And otherwise, we just take the function which you're summing and integrate it over the intersections of the hyperplanes, which we get here. And in order to evaluate this, we need an integral geometric transformation formula, which is well known in Euclidean space and which we proved also in hyperbolic space. And this gives an I-plane in an affine I-plane in the hyperbolic space. And using the next step, the Crofton formula due to brothers, essentially, we end up with the result. And this integral geometric transformation here and this one there, they are formally look the same in hyperbolic and spherical space, and that's why the formulas are the same in the end. So here's another ingredient in the central limit theorem, namely the variance. And the result is as follows. The variance of the intersection functional Fi within an observation window W is a sum with ingredients of the following type. So we have some constants. We have a monomial, which ranges from, this parameter n ranges from 1 to d minus I. That's the number of intersections of hyperplanes we are considering. And then we have such an integral, which is of Crofton type, but it's not exactly the classical Crofton formula because we have power 2 here. And this makes it much harder. And of course, for channel observation window W, averaging the volumes of these intersections raised to the power of 2 over all d minus n planes will not be expressible in a simple way in terms of W. But nevertheless, such integrals play an important role in stereology, and of course you can study geometric inequalities related to those. So which is surprising at first sight, this formula for the variance looks again similar to the Euclidean case, but there is some difference or major difference hidden in these so-called cross-sectional measures, which I want to explain now. So in Euclidean space, if you look at the asymptotic behavior of this measure, cross-sectional measure Jk, if W is a ball of radius r, so this asymptotic behavior is like r to the dimension of the space plus this index k. In hyperbolic space, the situation is different. So then it depends how big k is with respect to d. So if 2 times k minus I is smaller than d, the growth rate is like the volume, so e to the d minus 1 times r. If we have equality here, then you get an additional factor r. And if 2 times k minus 1 is exceeding d, then actually the growth rate changes again, and we get an exponent, additional exponent 2 up here, and the k here there. So we have these three cases, and if you look back at the variance here, then you see the growth rate with respect to the radius r of a ball, if w is a ball of radius r, will depend on these cross-sectional measures. And one observation which has to be made is that the dominating contribution comes from j d minus 1, which is actually the same in Euclidean space, as you can see from here. But then again, you have to distinguish these three cases for k equal d minus 1. And in each of those, you have a different growth rate. And so you get different growth rates if you translate this condition, and that condition, and they just correspond to the 3 dimensions 2, 3, and greater or equal 4. So this could be considered one explanation of a phenomenon which we are going to describe next or soon. But this is not the whole explanation. There's more to that. So maybe I'm skipping that. Here's a summary from the previous slides, which says that the variance of the I intersection functional behaves differently depending on the dimension of the space. So in dimension 2, with respect to the dependence on r, it's growing like the volume of a ball of radius r. In dimension 3, you get an additional factor, logarithm times of the volume. And in dimension 4, the additional factor is a volume of the ball raised to the power d minus 3 over d minus 1. Dependence with respect to the intensity t is consistent. It doesn't depend, it doesn't lead to a case distinction, but of course it also depends on the dimension and the intersection number. So this is actually the intersection number in a sense. So I wanted to make some comment on how this variance formula is proved, which we were using, or which we are needing. So that's only giving a brief impression. So once again, the functionals, the use statistics we are considering are of this form. And the kernel Fi is the Hausdorff measure of the intersection of d minus I of the hyperplanes intersected also with the observation window. And for any use statistic, actually there's a general result which tells you how the variance can be calculated. It's sometimes called the Fock space representation of use statistics. Also, it's related to the chaos expansion of general Poisson functionals. In any case, here's the formula, which is very general. And it tells you that you have some factor where the intensity enters, and certain L2 norms of functionals Fin, which are derived from this Fi. And they are derived in the following way. So Fi depends on d minus I parameters, and in considering Fin, you integrate out d minus I minus n of them with respect to the intensity measure here. Now, once you have accomplished the integration, you take the L2 norm. But maybe I go back here. This already shows you if you are managing to do some kind of integral geometric transformation, because here you get intersections of all these hyperplanes, then in fact you arrive again at the Hausdorff measure of some d minus n plane, here involving these intersections with the observation window. So in other words, the L2 norm of Fin is nothing else but the cross-sectional measure in the right dimension. And now if W is a ball of radius r, the main task in determining the growth rates of these expressions is not so easy looking at this expression, but let's introduce the precise form of the isometry invariant measure on the space of d minus n planes. So you get, if this is a ball of radius r, you get a sine hyperbolicus, you get the cosine from the weighting factor of, and then you have the volumes of the sections of the ball with d minus n flats having distance s from the center, so from the origin. And one task in finding the growth rates is to find sharp lower and upper bounds for these integrals.
Daniel, just one question.
Yes, question by whom?
Matthias Reitzler.
Yeah. Now I recognize your voice.
If you have a general convex body W and you increase this by a factor R, does it behave asymptotically like a ball, or is there different behavior if this is a special convex set?
Actually, we had a very hard time doing this for balls. And I'm not sure, actually. Of course, you could imagine that if you just consider scaling of a fixed shape, W.
Yes, that's what I meant.
Yeah, that you try to squeeze it, the W between two balls, and then, of course, expand also this inner approximation, outer approximation. But I guess in hyperbolic space, you will run into a problem because the surface area somehow has the same order like the volume itself. So I'm not sure whether this will really be helpful. Such a rough idea. So we didn't do that so far, actually. And I could well imagine that this will not work easily.
Okay, thanks.
Okay, so here's a first result, which looks nice, but somehow also disappointing. I will say what I mean by that. Because it's a central limit theorem for each of these intersection functionals. So we normalize and we actually prove, looking at that it satisfies the central limit theorem with the same rate as in the previous results you have seen. And actually it follows immediately from the results by Matthias, Schulte and Reitzler, because in a sense, here we fixed the observation window. That was the question, essentially, what Matthias was now asking. And we let the intensity go into infinity. And if you look at the statements of the tools, then you see essentially everything goes through like in the Euclidean case, and you do not have to change much once you have established the channel setting. So then you get a result, but it's maybe not very surprising. What is more surprising is what comes next, because now we start with dimension 2, the hyperbolic plane. We change the setting, so we keep the intensity T fixed, and we look at the expansion of the observation window, which are balls of radius r, so geodesic balls of radius r. And here again, we get a central limit theorem with rates and explicit expressions for the rates as r goes to infinity. This is, I should point out, not the same as what I mentioned before, that it doesn't matter whether we fix r and let t go to infinity, or we fix t and let r go into infinity, because hyperbolic space doesn't have natural scaling, and also the functionals don't. And you can see that this will not work by looking at the next result, where we consider hyperbolic 3 space. Again, T, the intensity is fixed. And we get a central limit theorem with explicit rates. But now the growth rate with respect to R, which was here essentially like e to the minus R over 2 times some polynomial in R, depending also at the moment on the choice of the index I. Which is here much slower. Now it's only like 1 over R or 1 over square root of R. So we still have a quantitative central limit theorem in dimension 3, but it's very much slowed down. And if we move on to dimension 4 and higher, the major surprise occurs, because here we could show that there no longer a central limit theorem holds. And more precisely, we showed that in dimension 7 and higher, there is no central limit theorem for any choice of I. And in dimension 4, 5, and 6, we could prove this at least in the top dimensional case, so for I equal to d minus 1. So here we could show that no central limit theorem is available. Now I see that my time is actually up, almost up to 2 minutes. So let me at least point out the next 2 slides. I guess this is okay, Elisabeth or Christoph?
Yeah, that's fine. You started a bit later also. And
Elisabeth somehow said, maybe I can take a little bit longer, but not too much, I guess. So I recall this result due to Matthias Reisner, Matthias Schulte, and also Matthias Schulte because he treated not only the Wasserstein distance, but later also the Kolmogorov distance. And I pointed out that we are winning the game of proving a central limit theorem once we are able to prove bounds for these ratios. So what we would like to do is lower bound the variance. And now you see why we strived to prove lower and upper bounds. So determining the asymptotic order of the variance of a Poisson statistic. And what we also need, and that's actually much, much harder in our case, to determine bounds for these expressions mu, v, which I have not explained so far. So just briefly, these functionals mu, v depend on the kernel of the Poisson statistic, and they are obtained by taking tensor products of these kernels, or what we derived from the kernels actually. So in these functions, you see the little r here, the radius of the ball enters. The intensity, t, enters in a way which is rather innocent and easy to treat because it's only multiplicative. So here, and that's showing you why the result where r is fixed and t goes to infinity is almost straightforward from what had been proved before. But the dependence with respect to the radius r of the balls, where we observe the intersections, that's much less straightforward. It's actually hard because we have to evaluate all these integrals, and they depend on certain partitions into blocks of the numbers 1 up to 2 times u plus 2 times v. So you see also, if u and v are increasing, you get more and more block or partitions of the set into blocks, and have to work harder, say. So in the simplest case, which is the 2-dimensional case, and I equal 1, that's the edge length functional. This simplifies a lot because then you have just one block, as you can show, and the integral we have to study can easily seen to be such a power integral. So we have the edge length of a line within the ball of radius r raised to a power of 4. And then this integral can easily be estimated in this way. But here you also see, now we are no longer having these cross-sectional measures with power 2, but we have some other power. And in the other cases which occur, you get actually products of Hausdorff measures of intersections of different hyperplanes. And all this has to be dealt with carefully to find the growth, the rates we could show. So in this special case where there's only one contribution, we just use the upper bound, take the square root, take the lower bound from the variance here, and this gives the result. But that's the easiest case. And nevertheless, I think now I really stop and wait for your questions.
Yeah, many thanks, Daniel.